Hello pre-calc honor students, here we are with probability of events occurring together. And the key word in this one is and. The probability of events occurring together and to determine whether two events are independent. And we're going to use the idea of and it's going to imply multiplication again, just as we saw in counting. Tree diagrams are going to be very useful because we have something called conditional probabilities we have to talk about. So first off, example 1. 2 yellow balls and 3 green balls are placed in a jar. One ball is randomly chosen, its color is noted, and the ball is put back in the jar. This is what we call replacement. This procedure is repeated for a second ball. Find the probability that both balls are the same color. So here's our tree diagram. First ball is either yellow or green. Second ball is either yellow or green. So what's the probability of yellow, yellow, and the probability of green, green? Both balls are the same color. So you have 2 yellow and 3 green. So that means yellow, yellow, green, green, green. Those are the balls in the jar. So the first ball being yellow is 2/5. Second ball being yellow, still 2/5 because you put that ball back. First one being green is 3/5. Second one being green is 3/5. So I put the conditional probability on the branches as we head out here. So notice this probability of y. We actually end up multiplying these two to get 4/5 to get to this leaf. This leaf is 9/25. I'm sorry, I should have said 4/25. So the probability of yellow then yellow is 2/5, the first ball is yellow, times 2/5, the second ball is yellow. The probability of green then green, 3/5, first ball is green, times 3/5, the second ball is green. So you get 4/25 plus 9/25 is 13/25. Now if we change this and do no replacement, that is, we're going to do the example again, but now the first ball is not put back in the jar before the second ball is chosen, and so things start to change a little bit here. Remember we had 2 yellows and 3 greens, so chance the first ball is yellow is still 2/5. First ball is green is 3/5. Now the second ball is yellow. Given that we pulled this first ball out and it was yellow, now we're only down to 1 yellow ball out of the 4 in there. The chance that the second ball is green then is 3/4. Here the second ball is yellow. Given that the first ball was green, we still have 2 yellows in there, but it's down to 2/4. And 2/4 for the green. So notice the probability of y changes now. It's 2/5. And the second ball is yellow is 1/4. And green, green then would be 3/5, first ball is green, times 2/4, the second ball is green. So you end up with 2/20 plus 6/20, or 8/20, which reduces down to 2/5. Notice not the same as our 13/25. Not nearly the same. So in both examples 1 and 2, we denote the probability that the second ball is yellow, given that the first ball is yellow, by this. We use this vertical bar. This is called conditional probability. It's spoken, the probability of A given B. So this vertical bar is designating whatever comes after is the new condition. Probability of event A given the condition that event B is true or has happened. B is like the new sample space for the probability. So in example 1, consider these. The probability that the second is green, given that the first is green. Let's get our old tree diagram back in example 1. Pause this for a second. Okay, here's our tree diagram from example 1. Now the probability that the second is green, given that the first is green, is 3/5. The probability that the second is green, given that the first is yellow, if the first is yellow, the second is green, that's still 3/5. The probability that the second is green. Now notice we get to green in 2 routes here. The second ball being green could be this route, which would mean 6/25. And this route, which is 9/25. And when I add those up, I get 15/25, which is 3/5. So notice the probability that the second is green is 3/5. And it doesn't matter what the first ball was because of our replacement. And so we call this independence. Now, probability the second is green is unaffected by the color of the first ball. So we call these two events, the second is green and the first is green, independent. Now watch what happens though when we consider example 2. And let's get our example 2 sketch back. Okay, here's our sketch from example 2. The probability the second is green given that the first is green. So we went green, now what's the chance that the second is green? Because we didn't replace in example 2, things have changed. So now we only have a 2/4 chance that the second is green, or 1/2. The probability the second is green given that the first is yellow. Well, the first was yellow, that's this direction, but now we have one less thing in there. So even though we have all 3 greens, there's only 4 balls left, so that's 3/4. Now let's look at the probability that the second is green. It comes from 2 spots. We can have a second ball green either this way, which would be 6/20, or if I go this route, 3/5 times 2/4 is 6/20. And when I add those two up, I get 12/20. And reducing that, we get, take a 4 out, 3/5. 3/5. Notice none of these are the same. There are dependencies here because we took the ball out. And so as a result, the probability the second is green is not equal to the probability the second is green given that the first is green. It depends. So therefore, these are dependent. It's affected by the color of first ball. We have a dependence between those two events. In general, two events A and B are independent if and only if the occurrence of A does not affect the probability of the occurrence of B. In symbols, A and B are independent if and only if the probability of B given A equals the probability of B. A happening does not change the probability of B. Now we can deal with and in probability questions. Probability of events occurring together. For any two events A and B, the probability of A and B equals the probability of A times the probability of B given that A has happened. You have to consider that A might be affecting B. You can also write this as, because the word and there is commutative, the probability of B times the probability of A given B. It can be done that way too, whichever one works out better in the situation. If events A and B are independent, then the probability of B given A is equal to the probability of B. So it just becomes this, and we end up multiplying the two probabilities together, like we did in example 1. Example 1. Now here's example 3. A card is randomly drawn from a standard deck. Show that the events Jack and Spade are independent. Okay, Jack and Spade. So the probability of a Jack is there's 4 Jacks in the deck. Out of the 52, that's 1/13. The probability of a Jack, given that it's a Spade, is, well, now we have a new sample space of only the 13 spades, and one of those is a Jack. Notice how these two are equal. The probability of Jack equals the probability of Jack given a spade, given that the card is a spade. Therefore, Jacks and Spades are independent. A lot of kids get confused about this because they think, oh no, the Jack and Spades overlap at Jack of Spades. That becomes important if we ask, what's the probability of a Jack or a Spade? We'd have to subtract over the overlap. But basically, a deck of cards is independent because of the symmetries you see in it. It doesn't matter what suit you're in, you're going to have the same ratio of Jacks. It doesn't matter what rank you're in, you'll have the same one card in each suit in each of the ranks. Now, use Rule 2 to find the probability of drawing the Jack of Spades. So the probability of a Jack and a Spade is the probability of a Jack times the probability of a Spade, given that it's a Jack. So, the probability of a Jack is 4 out of 52. The probability of a Spade, given that it's a Jack, well, now we have to look at the 4 Jacks in the deck, and one of them is a Spade, and we end up with 1 out of 52. And this makes sense. The Jack of Spades is just one of the 52 cards in the deck. But now, here's example 3, 1, 4, 1, 5, 2, 5, 3, 5. Example 3, repeat example 3 now. But this time, use a deck where Fido has eaten the Ace of Spades, making a 51-card deck. Oh, that Fido. Now the probability of a Jack is there's 4 Jacks in the deck. At least he didn't eat a Jack. But there's only 51 cards. Now, probability of Jack, given that it's a Spade, remember, given that it's a Spade, Fido ate the ace of spades, so now there's only 12 spades left, and one of them's a jack. 1/12 does not equal 4/51. 48 does not equal 51. Therefore, jack and spades are dependent events. Because the independence was ruined when the dog ate that card, it ruined the symmetry of the deck. So your chance of getting a jack changes depending on what suit you look in. If it's in spades, it's a 1/12 chance. If it's in all the other suits, it's a 1/13 chance. And also, if you just pull it out of the deck, it's only 4/51. These two don't match anymore. Now, there's another way to find conditional probabilities. I've been using this arrow technique and having you treat the thing after the vertical bar as the new condition. Well, there's a formal way to do this too. You could say the probability of B given A, take this equation, it's the probability of A and B divided by the probability of A. Okay? Visually, we can look at the number of elements in the overlap here. So this is the number in the intersection right here, like this, and divide it by all the elements in A, which is the big circle. Like that. That's our conditional probability. Now, let's look at this example 4. And each student in a class of 30 students, one world language and one science, studies one world language and one science. The students' choices are shown in the table below. So now we can start adding up these because we're going to need these row totals. 7 and 4, 11 and 3 is 14. 16 this way for a total of 30 students. That checks. 8 take chemistry, 10 take physics, and 12 take biology. We add those up, those also add up to 30. Now find the probability that a randomly chosen student studies chemistry. Well, for chemistry, we can look at the chemistry column. That's 8 out of the 30 students, which reduces down to 4/15. But 8 out of 30 is fine. Find the probability that a randomly chosen student studies chemistry, given that the student studies French. So now we have to just, given that the student studies French, now we can only look at the 14 French students. That becomes our new condition. So I'm only looking at this row. And in that row, how many study chemistry? 1, or 7. 7/14, which equals a half. A half and 4/15 are not the same. So we can see we've set up and established a dependency here. Are the events student studies chemistry and student studies French independent? No. The probability of chemistry is not equal to the probability of chemistry given that they study French. That makes them dependent events. Flange out.